Okay, let's jump right into a massive exam trap where Cambridge IGCSE computer science students are literally bleeding marks on network questions, despite actually knowing the material inside and out. I mean, you know how it is. You've memorized the textbooks, you completely understand the hardware, but then the results come back and you're just missing out on top band marks. Why? Because knowing the computer science is really only half the battle. The other half, it's knowing exactly how to translate that knowledge into the highly specific language the examiner is actually scanning for. Just look at this. It's kind of crazy, right? The exact same technical knowledge gets completely different marks, which reveals this hidden pattern in how the examiners greet us. On the left, a student who genuinely understands the concept writes it out casually, and they earn just 1 out of 4 marks. But on the right, they possess the exact same technical understanding, but they've structured their sentence to trigger the examiner's mark scheme checklist, securing a perfect 4 out of 4. So our goal today is to bridge that exact gap. All right, Section 1, Cracking the Command Words. To secure those top band marks in this explainer, we first need to crack the specific language Cambridge uses, because honestly, this is where the game is won or lost. There's basically a secret code examiners use that tells you exactly how much depth they want. When the prompt says state, they just want a concise, distinct point. No fluff whatsoever. When it says describe, well, that demands characteristics. What does the thing look like or what does it do? But when the prompt commands you to explain, that is the ultimate test. It requires the actual scientific why and how. You can't just say what is happening, you literally have to prove you know the underlying mechanical reality of why it's happening. So this framework right here is your safety net, guaranteeing you hit distinct technical points without accidentally repeating yourself. First, you identify the core concept. Second, look at the scenario or the evidence provided in the question. Third, apply your scientific reasoning. And finally, and this is absolutely crucial, translate that reasoning into precise examiner wording before you write down a single word. Moving on to Section 2, Unpacking the OSI reference model. We need a solid framework to make these networking clues completely obvious, starting with the foundational rules of communication. The OSI model is a vital conceptual framework designed to guide vendors so their digital communication products can seamlessly interoperate. Think about it for a second. How does a smartphone made by one company easily load a web page hosted on a server built by a completely different company using routers from a third company? Well, they can do this because of the Open Systems Interconnection, or OSI reference model. Understanding this model is very often a prerequisite for high-mark networking questions because it is basically the universal translator of the networking world. And really, understanding this model is absolutely essential because virtually all network troubleshooting and vendor operations rely on it. It provides a standardized roadmap. If a piece of network software is failing, engineers use the OSI model to isolate exactly where the breakdown is happening. It ensures that no matter who builds the hardware or writes the software, the end-user communication remains stable and standard. Okay, Section 3, Surviving Delay Distortion. The OSI model dictates how things should perfectly connect, right? But what happens when the physical layer of that model breaks down? Let's dive into our next high-stakes topic, what happens when network transmission goes wrong? Because in the real world, and especially in your exams, data just doesn't always arrive perfectly. So here is your syllabus-safe gold definition for delay distortion. It's actually quite simple. The signal literally changes its shape because different frequencies travel at different speeds through the wire. Remember, when we talk about guided media, we mean physical cables, like copper wires. When a complex digital signal is sent through these cables, it's actually made up of various frequency components. And here is the exact scientific reasoning you need for your exam. Those different frequencies absolutely do not travel at the same velocity. Notice the contrast here. The velocity is highest right near the center of the frequency band and much, much lower towards the edges, which is the root cause of the distortion. Imagine a group of runners starting a race at the exact same time. If the runners in the middle lanes are incredibly fast and the runners on the outer edges are much slower, well, that tightly packed group is going to spread out and lose its shape entirely by the time they reach the finish line. That is exactly what happens to a band-limited signal inside a cable. Walking through the steps, the mechanical timeline goes like this. First, the signal enters the medium. Because the velocity varies by frequency, the components soon arrive at completely different times. And boom, you're left with a physically warped and distorted signal compared to what was originally sent. Which brings us to Section 4, the examiner's mark scheme. Time to bring it all together and use our framework to actually beat the grading system. Here is a classic Cambridge scenario. Honestly, I want you to pause this explainer right now and just predict how you would score 4 distinct technical points here. Look closely at the command words, explain, and state. Think about our 4-step framework. What is the concept? What is the scientific reasoning? How are you going to articulate 4 separate, non-repeating points to grab every single mark available? All right, let's get the red pen out. The flawed, casual answer on the left barely gets 1 mark because it just lacks depth. The signal delays and changes shape. I mean, sure, it's broadly true, but it completely ignores the explain command. But look at how the improved answers securely locks in all 4 marks by hitting the precise technical vocabulary. It names the distortion, it explains the velocity variation, it ties it to frequency, and it states the consequence of parts arriving at different times. As you can see, examiners assign exactly 1 mark for each distinct technical point. You must systematically hit the name, the cause, the effect, and the result to get a perfect score without repeating yourself. If you write "the signal is slow" and then write "the signal takes a long time," you are only going to get 1 mark because to the examiner, it's the exact same technical point. Real quick, to keep getting these high-impact revision strategies delivered straight to you, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Okay, so you've got the framework now, right? But can you execute it under a ticking exam clock? We've solved the problem of what to write, but if you run out of time in the real exam, having the perfect framework simply won't save your grade. Having the perfect technical phrasing mapped out in your head is fantastic, but when the invigilator says you have 5 minutes left and you have a 6-mark networking question staring back at you, panic can completely destroy frameworks. To fix that exact problem, jump straight into our next explainer, where we're going to break down the exact time-to-answer writing system you need to deploy these answers flawlessly under pressure. Because knowing the answer is absolutely useless if you don't have the time to write it down. I'll leave you with this. Are you losing marks because of your knowledge or just because of your speed? Jump into our next explainer to master the ticking clock, and I'll see you there.